about these topics to understand Silvaco Atlas TCAD tool. So let's start. The first one is, what is Silvaco? Silvaco is a device simulation software which is used to obtain device characteristics like IV, CV, capacitance voltage, current voltage characteristics for the simulated device, which could be diode, MOSFET, TFET, organic device, and a lot of other device which are listed in the manual. The software comes with a set of examples which are listed in the manual, which are already discussed in the last presentation. At the end of this session, you should be understand the basic overflow of writing code in deck build and build their own structure whenever required. We can run the Atlas in three ways. Running Atlas inside deck build. To run Atlas inside deck build, use the following command file go atlas. Each Atlas run inside the deck build should start with the line go atlas. Second method is running a given version. To run any version, you have to specify the version name, in which we are running 5.14.0.r version. Go atlas simplex equal to version name. Running Atlas without deck build, you can run Atlas outside the deck build environment, but it is not recommended by the Silvaco. To run Atlas directly using Unix, use the command atlas input file name, atlas version name, and input file name. Next slide please. The order in which the statement occur in the Atlas input file is also important. There are five group of statements that must occur in the correct order. Otherwise, an error message will appear which may cause incorrect operation or termination of the program. For example, if the material model specification is set in the wrong order, then they may not be used in the calculation. The order of the statement within the group, that is structure specification, is also important. Otherwise, it may also cause incorrect operation or termination of the program. Different statements are divided into different groups. In structure specification, first you have to define mesh, second one is resin, third one is electrode, and the fourth one is doping. In the material model specification, first you have to define the material, then model, then contact, and after interface. In the numerical methods selection, you have to define the method, Newton method, Gourmet method, and next one is solution specification, in which you have to call save the log file, then use the source statement, then load, and after that save. In the result analysis, you have to extract the result using Tony plot. Next slide please. Defining a structure. There are three ways to define a device structure in Atlas. The first way is to read an existing structure from a file. The structure is created either by an earlier Atlas run or another program such as Athena or DevEdit. For example, mesh in file, we have to call the proper structure with the file name. The second way is to use the automatic interface. The automatic interface in deck build to transfer the input structure from Athena or DevEdit. The third way is to create a structure by using Atlas command language. Using the command language to define a structure, you must know about the deck build and the Tony plot. What is deck build? Deck build is an interactive graphic runtime environment for developing process and device simulation input decks. Second one is Tony plot. Tony plot is used to view the results. We used Tony plot to show the result in structure result as well as log file. We can see only in the Tony plot. Tony plot is a graphical post-processing tool for use with all Silvaco simulator and is an integral part of VWF interactive tool. VWF is Virtual Wafer Lab. Next slide please. Using the command language to define a structure. To define a device through the Atlas command language, you must define a mesh. The mesh or grid covers the physical simulation domain. The mesh is defined by a series of vertical and horizontal lines and the spacing between them, in which specifying the initial mesh using the first statement mesh space dot mult is equal to value. The space.mult parameter Value is used as a scaling factor or multiplying factor for the mesh created by the x.mesh and y.mesh statements. The default value is 1. Value greater than 1 will create a globally coarse mesh for the fast simulation. Value less than 1 will create a globally fine mesh for increased accuracy. When you do the coding in deck build, you can take the default value 1. In the left hand side of the plot, we have taken the value 1, and the right hand side of the plot, we have taken the value 0.5. You can see that when we have taken the value 0.5, then this figure 2 has double density in comparison to figure 1. It has double the density of the mesh in both x and y direction. Next slide please. Meshing continued. The x.mesh and the y.mesh statement are used to specify the location in microns of vertical and horizontal lines respectively, together with the vertical or horizontal spacing associated with the line. You must specify at least 2 mesh lines for each direction. Both negative and positive value of x and y are allowed. Next slide. Once the mesh is specified, every part of it must be assigned a material type. This is done with the reason statement. For example, reason number, integral, material type, and the position parameter. In this example, reason number is 1. The position parameter is specified by the x.minimum, x.maximum, y.minimum, and y.maximum. And the material type is the silicon in this example. Reason number must start at 1 and are increased for each subsequent reason statement. You can have up to 15,000 different regions in Atlas. A large number of material is available in the Silvaco TCAD. For a particular material, you have to study the Atlas manual. The position parameters are specified in micron using the x.minimum, x.maximum, y.minimum, and y.maximum statement. If the position parameter of a new statement overlap those with the previous reason statement, the overlapped area is assigned as the material type of the new reason statement. Make sure that material are assigned to our mesh point in the structure. If this is not done, error message will appear and Atlas would not run successfully. Next slide please. Third, define the electrode. Once you have specified the reason and material, define at least one electrode that contacts a semiconductor material. This is done with the electrode statement. For example, electrode name, we have to specify the electrode name, gate, drain and source, and the position parameter. In this example, we have taken the electrode name gate, and the position parameter is specified by the x.minimum, x.maximum, y.minimum, and y.maximum. You can specify up to 50 electrodes. The position parameter are specified by the x.minimum, we have already mentioned. Multiple electrode statements may have the same electrode name. Nodes that are associated with the same electrode name are treated as being electrically connected. Some shorts can be used when defining the location of an electrode. If no y coordinate parameter are specified, the electrode is assumed to be located on the top of the structure. You can use the right, left, top or bottom parameter to define the location. For example, electrode name, source, left, length is equal to 0.5. This statement specifies the source electrode starts at the top left of the corner of the structure and extend to the right of the distance length 0.5 micrometer. Next slide please. The final step is to specify the doping in each region. You can specify analytical doping. You can specify analytical doping distribution or have Atlas read in profile that come from either process simulation or experiment. You specify the doping using the doping statement. For example, doping, distribution type, dopant type, and the position parameter. In this example, we have taken the n-type concentration, and the concentration is equal to 1E18, and the distribution type is uniform, Analytical doping profile can have uniform, Gaussian or complementary error function. Two examples are shown below with the combined effect shown in figure. Doping uniform. First one, uniform doping profile. Doping uniform N-type concentration is equal to 1E18 in the region 1. And the second Gaussian doping profile, doping Gaussian concentration equal to 1E18, characteristics is equal to 0.05, P-type, x dot left 0.0, x dot right 1.0 and peak 0.1. The first doping statement specify a uniform N-type doping density of 10 to the power 18 per centimeter cube in the region 1. That was previously labeled as region 1. The position parameter x dot minimum, x dot maximum, y dot minimum and y dot maximum can be used instead of the region number. The second doping statement specify a P-type Gaussian profile with a peak concentration of 10 raised to power 18 per centimeter cube. This statement specify the peak doping is located along a line from x is equal to 0 to x is equal to 1 micron. Perpendicular to the peak line, the doping drop off according to the Gaussian distribution with a standard deviation of 0.05 divided by under root 2 micrometer. For more information, you can go to the Atlas manual and find the different parameter value. Next slide, please. Specifying 3D structure. The syntax for forming 3D device structure is an extension of 2D structure described in the previous section. The mesh statement should appear as mesh 3.d. The 3.d parameter tells Atlas that a three-dimensional grid will be specified. The other statement used to specify 3D structure and grid are the same as 2D with the addition of Z direction specification, in which simply Z mesh location is introduced. We have to define X mesh, Y mesh as well as Z mesh. Define a 3D mesh that is uniform in X and Z direction and varies in the Y direction. Position parameter for the Z direction are also used in region, electrode and doping statement. It is important. You must specify the Z location in the region, electrode and doping statement. As mentioned in the previous section, using the command language to define a structure, you can model a 3D cylindrical structure in Atlas 2D by specifying the cylindrical parameter on the mesh statement. In Atlas 3D, the cylindrical parameter enable you to create a general cylindrical structure. The mesh statement must appear as mesh 3.d cylindrical, where the 3.d parameter inform the simulator to create a fully 3D mesh. When specifying the cylindrical parameter, you must now specify the structure in terms of radius r dot mesh, angle a dot mesh and z coordinator in the form of z dot mesh. There are three mesh statements are analog to those used for the general structure that are used to specify mesh in radius, angle and z direction. The r dot mesh statement is used to specify radial mesh. The a dot mesh statement is used to specify angular mesh. The z dot mesh statement is used to specify mesh in the z direction. In the example, you can see we have defined mesh 3.d cylindrical, meshing in three form r dot mesh, a dot mesh and z dot mesh. Here the r dot mesh lines are similar to the familiar x dot mesh, y dot mesh and z dot mesh, except that r dot mesh location and spacing are radial relative to the z axis in micron. The location and spacing on the a dot mesh line specify location and spacing in degree of rotation about the z axis. The z dot mesh lines are exactly the same as we have already been discussed in the last slide. Next slide, please. extracting 2D structure from the 3D structure. To simulate circular structure in 2D that are analogous to the 3D meshing described above, use the cut plane feature in the structure saving. We will discuss about it in my next presentation. The next presentation is about how to make a nanowire structure, in which we are discuss the 3D structure in details. Next slide please. Specifying a good meshing or grid is a crucial issue in device simulation, but there is a trade-off between the requirement of accuracy and numerical efficiency. Accuracy requires a fine grid that resolve the structure in solutions. Numerical efficiency is greater when fewer grid points are used. You must take care about the critical area when you define meshing. Typical critical area are high electric field at the drain channel junction in MOSFET, the transfer electric field beneath the MOSFET gate, recombination effects around the emitter base junction in BJT, area of high impact ionization around heterojunction in HBT and HEMS. The three most important factors to look for in grids are: the most effective way is to allocate a fine grid only in critical area and a coarse grid elsewhere. You have to take care of these 3 points. Ensure adequate mesh density in the high field area, for example junction area. Avoid obtuse triangle in the current path or high field area. And the third one is avoid abrupt discontinuity in the mesh density. This means you cannot change the mesh spacing from minimum value to high value or high value to minimum value. Once you define the mesh geometry and the doping profile, you can modify the characteristics of electrode by change the default material parameter and choose which physical model atlas will use during the device simulation. To accomplish these actions, use the contact, material and model statement respectively. In the next slide, we will discuss about how to define a contact and how we can introduce a new material and which models are available in the Atlas manual. We will discuss in the next slides. Impact ionization model can be enabled using the impact statement. Interface properties are set by the interface statement. Next slide please. In this slide, we will talk about how to define a contact. Work function for gate or Schottky contact. An electrode in contact with the semiconductor material is assumed to be by default to be ohmic if the work function is not defined. If a work function is defined, the electrode is treated as a Schottky contact. For example, the statement contact name gate work function is 4.8. The contact statement is used to specify the metal work function of one or more electrode. The name parameter is used to define which electrode the work function is applied. The work function parameter set the work function of the electrode. For example, this one. This example show that set the work function of the electrode name gate to 4.8 electron volt. The work function of several commonly used contact material can be specified using the name of the material. This means we can also specify the work function by the name of the material. You can specify the work function as aluminum and polysilicon, tungsten, etc. in this way. You can see from this example in which we have mentioned the work function, the name of the material, N dot polysilicon is applied. One more thing, aluminum contact on heavily doped silicon is usually ohmic. For this situation, don't specify a work function. The contact statement can be used to specify barrier and dipole lowering of the Schottky barrier height. To enable barrier lowering, specify the barrier parameter while specifying dipole lowering using the alpha parameter. For example, you can see contact name, anode, work function, barrier, alpha, 1E-7. This statement set the work function of the Schottky contact named anode to 4.9 electron volt. This will enable barrier loading and act the dipole loading coefficient and set the dipole loading coefficient to 1 nanometer. One most important thing, when a Schottky barrier is defined at a contact, we recommended that a fine mesh is at Y is present. This allows the Schottky depletion region to be accurately. Next slide please. Schottky to contact together. It is possible in Atlas to tie two or more contacts together so that voltage on both contacts are equal. This is useful for many technologies, for example dual base dipole transistor. If the structure is defined using Atlas syntax, you can have multiple electrode statements with the same name parameter defining separate location within the device structure. In this case, the area defined to be electrode will be considered as having the same applied voltage. A single current will appear combining the current coming from both electrode area. For example, voltage applied to the two electrode, gate and gate 1. Contact name gate 1 we have common with the gate terminal. We are applying the voltage in the solve statement V gate 0.1. Here the electrode gate 1 will be linked to the electrode gate. This means we are applying the voltage 0.1 at the gate terminal will come on both the gate terminal. The applied 0.1 volt on gate will then appear on gate 1 also. Next slide please. Specifying material properties. All materials are split into three classes: semiconductor, insulator and conductor. Each class requires a different sets of parameters to be specified. For semiconductor, the material statement must include electron affinity, band gap, density of state and the saturation velocities. These are the default parameters for the material property used in the device simulation for many materials. For more information, you can go for the Appendix B material statement in Atlas manual. List default material parameter and include a discussion on the difference between the specifying material for semiconductor, insulator and conductor. If you are not using the material statement and the material you are specified in the Atlas code is already present in Atlas manual, then it can take the default value. If you want to change this default value, you have to introduce the material statement. The material statement allow you to specify their own value for these basic parameters. Next slide please. The material statement allow you to specify your own value when you are introducing your new material or you are changing the parameter of already defined material in the Atlas. For example, the statement material silicon Eg at 300 1.12 electron volt MUN represent the mobility of electron. If the material property are defined by region, the region is specified using the region or name parameter in the material statement. For example, material region 2 TANU 2E-7 TAUP 1E-5. TAUN specify the lifetime of electron in trap level. TAUP specify the lifetime of hole in the trap level. TAUN and TAUP define the bipolar device. Next slide please. Specifying interface properties. The interface statement is used to define the interface charge density and surface recombination velocity at the interface between semiconductor and insulator. For example, statement interface QF 3E10. This statement specifies that all interface between semiconductor and insulator have a fixed charge density of 3E10 per centimeter square. In many cases, the interface of interest is restricted to a specific region. This can be accomplished with a position parameter statement: x dot minimum, x dot maximum, y dot minimum and y dot maximum parameters on the interface statement. These parameters define a rectangle where the interface properties apply. For example, interface QF 310 position, these are the position parameter. This statement restricts the interface charges to the semiconductor insulator boundary within the specified rectangle. In addition to the fixed charge, surface recombination velocity and thermonic emission are enabled and defined with the interface statement. Yes, in this presentation, one thing is pending, that is how to specify physical model in Atlas code. This will be studied in the next presentation. Okay, my dear friend, that is it.